Russia and Alaska are separated by only 85 kilometers of Arctic water. But any permanent crossing would have to survive moving sea ice, powerful currents, uncertain seabed conditions, and some of the harshest operating conditions on Earth. And even if engineers crossed the strait, the structure would still end hundreds of miles from a complete transportation network. So the real question is not whether we can build the bridge, it is whether we can build everything required to make it useful. At the western edge of Alaska, North America faces the eastern coast of Russia across the narrow gateway between the Pacific and Arctic Oceans. Between them lie Big Diomede and Little Diomede, two remote islands separated by roughly 4 kilometers and divided by an international border. On a map, the opportunity appears extraordinary. A permanent link here could create the first direct surface transport connection between Eurasia and North America. Its most credible form would probably begin with freight rail rather than an exposed highway. A protected railway could move cargo through a controlled corridor while also carrying power and communication systems between the continents. But the safest crossing may not remain above the water for its entire length. Before choosing a bridge, a tunnel, or some combination of the two, planners would need to answer a more basic question. Why build it at all? The strongest argument is freight. A continuous overland route might serve cargo that benefits from rail transport, provided the entire system could operate reliably and competitively. It could also allow several infrastructure systems to share one corridor. But distance alone cannot justify the project. Container ships already connect established ports supported by mature roads, railways, warehouses, and industrial centers. A train using the Bering route would face a much longer chain. Cargo would need to cross northeastern Russia, pass beneath or above the strait, travel through western Alaska, and continue across Canada before reaching the largest North American markets. The route would also need customs systems, border security, maintenance bases, compatible operating standards, and year-round reliability. The project needs more than a spectacular structure. It needs a cargo market large enough to support an entire Arctic transport system. The geography creates another illusion. The Bering Strait is relatively shallow for a major marine crossing, averaging roughly 50 meters in depth. Detailed mapping of part of the Eastern Channel has identified depths of approximately 54 meters. Those numbers are challenging, but not beyond modern marine construction. The deeper uncertainty lies beneath the seabed. Water generally flows northward from the Pacific into the Arctic. Strong winds can temporarily alter or reverse that movement. As currents pass through the strait, they can transport sediment along the bottom. When water accelerates around a bridge foundation, it can remove the material supporting that foundation. This process is known as scour. A pier can be strong enough to carry the bridge and still fail if the seabed around it is gradually washed away. A comparison between older and newer surveys indicated approximately 1 meter of apparent seabed lowering across much of the measured Eastern Channel. Although the data sets have important limitations, that does not prove the entire crossing is eroding at the same rate. It does show why engineers could not design the foundations from a map alone. They would need sonar surveys, boreholes, sediment sampling, current measurements, ice observations, and long-term monitoring before selecting an alignment. The water may be shallow. The foundation problem is not. The most dramatic solution would be a continuous bridge from Russia to Alaska. Instead of relying on a few record-breaking spans, engineers could use a long sequence of standardized viaduct sections. Large segments might be fabricated in coastal assembly yards, carried offshore by specialized vessels, and installed during limited periods of favorable weather. The foundations could use deep piles or massive caissons. Above the water, sloped piers could force moving ice upward until it fractured, rather than resisting it against a vertical wall. Larger spans would leave navigation channels open, while a protected railway deck could reduce exposure to wind, snow, and freezing spray. None of these technologies is new on its own. The challenge is combining them across 85 kilometers of Arctic water. A continuous bridge would reduce underground construction, but it would leave a vast number of foundations, joints, bearings, and exposed structural components directly inside the marine environment. A second option would use fewer, longer spans. Cable-stayed or suspension sections could reduce the number of foundations and create wider navigation clearances. But the difficulty would move upward. Long spans require taller towers, larger anchors, heavier cables, and a more flexible deck. In Arctic conditions, those components would face wind, icing, temperature changes, vibration, and difficult inspection access. Every bridge solution removes one problem by increasing another. That is why the strongest concept may not be a conventional bridge at all. The most credible fixed link could combine marine viaducts with deep bored tunnels. In shallow areas with suitable foundation conditions, engineers might use repeated bridge sections. Near major navigation channels, poor seabed conditions, or locations exposed to the most dangerous ice forces, the railway could descend beneath the seabed. A tunnel would avoid direct ice impact, freezing spray, surface wind, and collision risk from passing ships. Inside it, trains and utility systems could operate in a controlled environment. But underground construction creates three major challenges. The first is water control. The tunnel would need waterproof linings, drainage systems, pumping stations, and redundant power to prevent leaks from becoming a system-wide emergency. The second is fire and ventilation. A freight train fire could fill a long section with smoke, while a disabled locomotive could block one of the running tubes. Ventilation systems would need to control smoke and preserve a safe evacuation path. The third is escape and redundancy. The safest arrangement could require two railway tunnels connected by frequent cross passages, supported by emergency refuges, service access, backup communications, and independent power systems. If one tube became unsafe, crews could move into the parallel tunnel. The Diomede Islands may appear to offer convenient intermediate access points, but using them would involve sovereignty, environmental review, community interests, worker safety, and difficult logistics. They cannot simply be treated as empty construction platforms. A bridge-tunnel hybrid would not remove the project's risks. It would separate them. Bridge sections would avoid unnecessary tunneling. Tunnel sections would protect the route from the most dangerous surface conditions. The final crossing might look less like one heroic bridge and more like a connected system of viaducts, tunnels, transition structures, pumping stations, ventilation plants, and emergency facilities. That complexity may be exactly what makes it technically conceivable. The safest bridge across the Bering Strait could be partly underground. Even then, the exposed sections would still face sea ice. And sea ice is not one predictable load. It can form along the coast, break into moving sheets, accumulate into pressure ridges, and become driven by wind and current. A pier might experience thousands of smaller contacts, followed by a much more severe event when ice builds across a wider area. Changing Arctic conditions do not make that challenge disappear. More open water can expose the crossing to stronger waves. Later, freeze-up can change construction and maintenance windows. Mobile ice may behave differently as wind, temperature, and ocean conditions shift. Less predictable ice does not necessarily mean less dangerous ice. Critical piers could use ice-breaking geometry, reinforced foundations, replaceable protective components, and real-time monitoring. But surviving Arctic loads is only half the problem. The structure must also survive time. Salt water would attack it throughout its operating life. Chlorides can penetrate concrete and reach reinforcing steel, allowing corrosion to develop inside the structure. Steel components would face coating damage, fatigue, moisture, and repeated temperature cycles. Bearings, joints, cables, pumps, ventilation systems, electrical equipment, and sensors would eventually need repair or replacement. The crossing could not be designed only for strength. It would have to be designed for access. Workers would need internal routes through piers and decks. Critical components would need to be replaceable. Spare equipment might have to be stored near the crossing because delivering it after a failure could take too long. Drones and robotic inspection systems could reduce exposure. They could not remove the need for human repair crews operating in one of the most isolated environments on Earth. Building the crossing may be possible. Keeping it safe for generations could be harder. Then the structure would reach land. On the Alaskan side, it would arrive at the Seward Peninsula. The region has local roads around Nome, but it is not connected to the rest of Alaska's continuous road system. A previous Alaska transportation study examined an approximately 550-mile corridor, nearly 900 kilometers, between the existing highway network near Manly Hot Springs and the Nome area. That study was not a Bering Strait bridge plan. It was not a transcontinental railway design. It simply reveals the scale of the missing connection. A functioning boring corridor would require new railways, bridges, power systems, communications, supply ports, maintenance depots, worker camps, emergency bases, and border facilities across western Alaska. A similarly large program would be required across Chukotka before the crossing could connect efficiently with the wider Eurasian transport network. The bridge would be the visual centerpiece. The approach corridors could become the larger mega project. On land, the problem changes again. Much of the route could cross permafrost. Frozen ground can support infrastructure while it remains frozen. But when ice-rich ground thaws unevenly, the surface can settle. Drainage patterns can change. Embankments can deform. Railway tracks can move out of alignment. For heavy freight trains, even small changes in geometry can create serious safety and maintenance problems. Construction itself can disturb the surface layer that helps insulate the frozen ground. Engineers might respond with elevated foundations, insulated ground systems, and continuous temperature and settlement monitoring. But no single method would necessarily work across the entire corridor. Each section would have different soil, drainage, ice, and thermal conditions. The sea crossing would be difficult to build. The land corridor could be difficult to keep level. The Bering Strait is also not an empty industrial frontier. Water passing through it carries heat, freshwater, nutrients, and marine life from the Pacific into the Arctic. The wider Bering Sea region is home to more than 70 indigenous communities whose food security, travel, culture, and local economies are closely connected to sea ice and marine ecosystems. Construction could disturb the underwater environment through noise, seabed work, vessel traffic, and spill risk. Permanent industrial infrastructure could alter coastlines, require power and access roads, and introduce long-term activity into remote areas. The project could also transform nearby communities through new border systems, outside labor, and changes to transport and local economies. These consequences could not be treated as paperwork completed after the engineering design. Local and indigenous participation would need to influence the route, construction methods, operating rules, emergency planning, and the decision over whether the project should exist at all. A structure is not buildable simply because its materials can carry the load. It must also be acceptable to the people and ecosystems expected to live beside it. Then comes the question that defines almost every mega project. What would cost more? The crossing itself, or everything required to reach and operate it? No detailed, independently validated concept design currently exists for a complete Bering Strait fixed link. Without a selected route, a geological model, a transport plan, and a freight forecast, no defensible total estimate exists. The program would need to be priced in layers. First, the marine bridge tunnel crossing. Second, regional infrastructure including ports, power, maintenance facilities, and emergency bases. Third, the continental railway connections required to make the crossing useful. And finally, the cost of operating and maintaining the system for generations. The same uncertainty applies to time. This would not be a single bridge contract. It would be a multi-decade international program involving geological research, environmental review, indigenous consultation, financing, diplomacy, design, logistics preparation, construction, testing, and long-term operating agreements. The schedule would depend less on how quickly engineers could install a bridge segment and more on whether two countries could maintain cooperation through many years of planning and construction. The project would require shared standards for rail operations, customs, safety, security, emergency response, inspection, financing, and maintenance. It could fail without a single foundation ever being poured. So, could we build a bridge across the Bering Strait? The Buildability Index examines 5 areas. This is an editorial engineering assessment, not an official feasibility result. Technology receives 12 out of 20. The component technologies already exist independently. Engineers know how to build marine bridges, offshore foundations, bored tunnels, protected railways, ice-resistant structures, and monitoring systems. But they have never been combined at this scale, in this location, with this level of isolation. Materials receive 12 out of 20. Modern steel and concrete could resist many of the required loads. The greater challenge lies in corrosion, fatigue, ice damage, repair access, and long-term replacement. Economics receives 5 out of 20. There is no proven freight market, selected route, or defensible total cost. The infrastructure required on land could become more difficult and more expensive than the crossing itself. Environment receives 7 out of 20. A tunnel-heavy route might reduce some surface impacts, but no alignment could avoid major ecological, cultural, and community concerns. Politics receives 4 out of 20. The project would require durable cooperation between the United States and Russia over borders, security, financing, engineering standards, customs, emergency response, and maintenance. That gives the Bering Strait fixed link a buildability score of 40 out of 100. The project does not violate the laws of physics. A rail-first bridge tunnel system appears technically conceivable using extensions of existing engineering, but it is not currently buildable as a complete transportation system. Before construction could begin, it would need a proven economic purpose, extensive geological investigation, a credible environmental strategy, meaningful indigenous participation, and international cooperation capable of lasting for generations. The narrowest gap between Asia and North America is only 85 kilometers wide. But the true distance is measured in frozen coastlines, missing railways, unstable ground, environmental responsibility, economic uncertainty, and political trust. The bridge may not be the most difficult structure. The real challenge would be building everything required to make that bridge matter. This is where Arctic engineering meets the limits of global cooperation,
technically conceivable,
and where connecting two continents becomes far more difficult than crossing the water between them. Which impossible megaproject should we investigate next?